And excellent. So look, I just realized I needed to launch that poll. So if you haven't already done so, there is a online poll within the Zoom window. You'll find it just next to the Q&A. And basically we've asked two questions, and those are the questions there. So you can fill the answers to those questions in at any time. And we're going to talk about the results at the end of the webinar. Hopefully, if we can get the results live. I've never done this on Zoom, so we'll see how we go. But look, let's get the show on the road. So thank you all very much who are in attendance today. And I see we've already got about 160 something in attendance, and I suspect that number will grow because everyone sort of rushes in the next 2 minutes. But this is the topic. Does bioretention actually work? And myself and Mike will be presenting today. As I indicated before, we do have an online poll, which you can complete at any time. And we're certainly interested to know the results of that, to basically get your feedback as well. And obviously you can provide comments in the chat bar. And obviously we're going to more than likely have a whole bunch of questions that people want to put forward to us. And you're certainly welcome to do so at any time. Generally find the people that ask the questions first are the ones that get their answers first. So if you have got any questions at any time, please do so. And look, first and foremost, we know we've got a conflict of interest in this regard, in this topic. So for many years, we've been putting in Ocean Protect and previously Stormwater 360, we've been putting in proprietary stormwater treatment devices, which can be seen as an alternative to conventional bioretention. And we don't shy away from that. We're very proud of that. But also we do have an alternative to conventional bioretention, which we call Filtera bioretention, also referred to as high flow bioretention. And there's an increasing number of those being put in around various urban environments in Australia. But it's a technology that's been in the US for about 15 years as well. So they're our conflicts of interest. So and I guess to mitigate some of that potential bias, in all the sort of papers I present, I give full references. And I certainly encourage anyone who's tuning in to actually go undertake their own research as well. I guess something to keep in mind also is that pre-Ocean Protect, I was putting in bioretention systems for about 15 years. So I think I've probably got a bit of a bias in that I really hope they actually do work. So look, I'd like to think I'm a little bit Switzerland on this issue, but I'll leave it up to others to decide. How this I guess topic and research was essentially initiated was I came across this report just recently. It was a report for the Victorian EPA and was prepared by the CRC for Water Sensitive Cities and Alluvium, etc. And they basically did a review of stormwater science. And whilst I guess the Vic EPA guidelines very much encourage bioretention systems and wetlands and other vegetative systems, this report said this, and I'm quoting it here: analysis of the performance of biofiltration systems suggests treatment performance is variable. And that, I guess, it got me sort of really questioning as to why a group would be advocating in the Victorian EPA, why would a group be advocating for these bioretention systems if they're, at least seemingly from this report, there was a real, I guess, cloud of doubt over their performance, or at least highlighting the fact that their performance of bioretention systems is variable. So that basically sent me down the rabbit warren hole of investigating, okay, how variable is it? Do bioretention systems actually work? And this has, I guess, been the formation of this webinar. So this is what I'm going to talk, this is what myself and Michael are going to talk about today. We're going to talk about what are the objectives of bioretention, how do they work? I'm going to talk about the lab scale studies of conventional bio, and also how that data from those studies is actually transitioned to the field. And then I'm going to talk about field scale studies of bioretention systems. And I'm going to separate them into both conventional bioretention systems and high flow bioretention systems. And on the basis of that, provide a few recommendations as well. So I guess to start with, bioretention systems are kind of like cars in that they come in all shapes and sizes, but generally have I guess, a fairly consistent sort of objective. In that cars trying to get us from A to B, or transport goods from A to B, but obviously come in different shapes and sizes and configurations, various different design objectives and standards, etc. And like cars, bioretention systems can fail for any number of reasons. So, for example, if a car isn't designed and built properly, yeah, you probably expect it to sort of fail. If it's asked to do more than it's actually designed to, like carry a load greater than it's actually designed for, it'll probably struggle as well. If it's applied in the wrong environment, it'll probably fail. And like anything, if it doesn't get maintained, it'll probably won't work as well as it would otherwise. But obviously, objectives, in terms of the objectives of bioretention systems, like there's a range of objectives, but this is probably the key objective. And this comes straight out of the Water by Design bioretention technical design guidelines. And they state, and I'm quoting them here, the key function of biofiltration systems is to remove pollutants from stormwater. Now, obviously, bioretention systems can provide other benefits in terms of amenity, passive irrigation, reducing the frequency and volume of stormwater discharges from urban environments. But again, the key function of bioretention systems is to remove pollution. So that's, I guess, when I'm asking the question, do bioretention systems work? I'm really focusing on that particular objective. And when it comes to these objectives, generally across Australia, where urban development is tasked with achieving what we refer to as average annual load removal targets. And they're focused on, I guess, 4 key urban stormwater pollutants in total suspended solids, total phosphorus, total nitrogen, and gross pollutants. And depending on where you are in the country, these are essentially the targets. So TSS, 80 to 85% annual load removal. Total phosphorus somewhere between 45 and 65, total nitrogen generally 40 to 45, and gross pollutants 70 to 90%. So obviously there's a whole bunch of other pollutants within stormwater, but these, I guess, are the ones we are tasked with when it comes to at least new urban environments.
Yes, and it's quite a rudimentary measure as well. You know, this is stormwater. This is not wastewater. We don't have the same volume every day. It's storm flow. We have high concentrations, low concentrations. We have different speciations of nutrients. We have different hydrology. You know, it's not, and these are very rudimental numbers. So it's quite a crude measure, but it's the measure that we currently have. But yeah, it's just quite difficult because these numbers here don't really paint a picture of everything that's going on.
Mm. In terms of how they work, like I think you can essentially assume they act like a box. You know, if you got flow coming in, something happens in that box and flow comes out and some sort of pollution is removed. And you might go, you know, okay, that's a box, but it's a good box. It's like a Volvo. They're boxy, but they're good. But if you want to go into the detail of how a bioretention system functions, yeah, there's a whole bunch of things going on. There's a whole bunch of physical, chemical, and biological processes that act to essentially decay or remove pollution from stormwater. And I've sort of listed them all on there on the right-hand side. But you expect some of those would actually change, particularly the biological treatment processes would change with various climatic conditions, preceding rainfall conditions, etc. But yeah, there's a whole bunch of physical, chemical, and biological processes in place when we talk about removing pollution from stormwater. One thing to keep in mind is there's been a little bit of talk just recently around water losses, in that where some of the field monitoring has shown that, yeah, bioretention systems show significant water losses. And there's a real question mark as to whether they were acting like sponges and just evapotranspiring that water out, and with significant volume losses. But look, there was a recent paper just put out just recently by the CIC for Water Sensitive Cities, authored by a whole bunch of, I guess, eminent people in the stormwater industry. And they basically, and this report is publicly available, it's on the internet. I can flick you guys a link afterwards if you like. But look, they made a few key conclusions based on their analysis. So number one, but bioretention systems act like filters and they do not act like sponges. And any observed losses that we have seen in bioretention systems are essentially dominated by exfiltration. So exfiltration water isn't lost, but it's just seeping into the surrounding soils and groundwater. And so, and any losses that we do see due to evapotranspiration are reliably predicted by long established equations. So if you took a typical bioretention system and modeled it in music, yeah, music would generally predict an evapotranspiration loss of about 2 to 5% of the incoming flow volume. That's assuming that the system is appropriately sized to meet local targets, etc. So music is, yeah, a reasonably good predictor of evapotranspiration loss. So it's worthwhile noting in the studies I refer to, I do talk about concentration loss, but you probably expect that the load losses would be slightly higher than the concentration losses. But certainly those losses aren't massive in terms of evapotranspiration loss. Certainly water seeping into the groundwater and into the soil profile and making its way very slowly into the waterway or other sort of aquifer, etc., is a good thing. It's acting to protect our waterways to some extent, but that water just isn't magically lost or evapotranspired.
Yeah, and I think, Brad, just on that, look, we've done a lot of testing of cartridge filters, whether it be the different products, jellyfish, storm filter, and one common issue with some of the tanks being in the field is they leak. They're just leaky systems. And depending on the subsoil surrounding your treatment system, whether this is bioretention or it's a cartridge filter, water, yeah, as you said, it's not lost from the system, but it's more or less a leaky well, more or less. And that's, the findings of the report similar to the findings that we've had in the field by looking at these systems over the past 19 years. So, yeah, the losses that we're seeing, in bioretention, is certainly not at the 50-odd% sort of margin. And number two, the equipment that you'd actually do to field test and measure flow reductions, you've got 2 to 5% error on all your equipment. And so you compound that on the inlet and outlet side, you've got huge errors here. So I think certainly there's error in the equipment, there's error in the methods. I think that music in this case probably does a good job of predicting how much water we're losing from the systems.
Cool. Let's dive straight into the lab studies. And I want to talk about lab studies. I'm talking about microcosms and sort of mesocosms that actually aren't really treating real world stormwater. And so probably people have seen a whole bunch of, images of column experiments and those sort of things and willy bin experiments. And that's kind of what I'm talking about. So, and in the eWater Music User Guide, they refer to a whole bunch of lab studies, and I've referenced them all here. But it's also worth noting that there's been quite a few additional lab studies that aren't referenced in the Music User Guide. And I've listed them all here as well. Again, you're welcome to do your own research around these papers, but I'll essentially summarize them as best I can. So, but essentially in summary, these lab-based studies are essentially using young bioretention systems. They generally use a semi-synthetic stormwater, so not a real stormwater volume, but like a synthetically developed stormwater. And they generally have a range of dosing frequencies and a range of media types. And they also use submerged zones, and a lot of the systems don't have submerged zones. They use a range of vegetation species. And if you look at the Monash University studies, they're generally sized based on a system size of roughly 2 to 2.5% of the upstream catchment. And that's for Melbourne catchment conditions as well. In terms of the results of these studies, again, just summarizing them as best I can, generally, we see high TSS, total phosphorus and heavy metal concentration reductions. The total nitrogen concentrations are variable, but they generally are high for sandy loam media with effective plants, essentially the media and the plants that we would essentially recommend in today's standards. And generally the total nitrogen removal is enhanced by the addition of a saturated zone. Again, this is pretty consistent with what the advice is in various industry guidelines now. So that's the lab studies. And the recommendations from these studies are essentially what we adopt in the industry today. Plant species which maximize nutrient removal. A saturated zone may assist with nitrate and TN removal. A sandy loam media is probably a good media to use, and ideally without any additional organic matter. And generally the studies actually say that these systems should be sized to at least 2% of the catchment area. So, and I know in Queensland, we often size these systems at say 1.2%. In Sydney, it's often lower. In Melbourne, it's lower again. I think it's fair to say that those sizes are significantly smaller than what is recommended in those lab studies. But a key thing to consider, I'm sure everyone sort of would acknowledge this, and I'm quoting one of the papers here, is and I'll quote it, that the magnitude of reductions reported in the current paper cannot be extrapolated to field conditions without validation. So I guess this paper in particular is saying, yeah, we've got some lab scale results, but I wouldn't extrapolate those to, I guess, to predict real world performance of bioretention systems without appropriate validation.
Yeah, and just a caveat on this lab testing. Remember, these are highly controlled tests, and any device tends to behave in a lab. Remember, the specific blend of the media would be absolutely bang on the specification. Same with the plants using and the planting. You know, there'd be a maturation period. Everything is set up. The methodology is standard. Everything is running like clockwork, more or less, in a lab. You take that to a field, there's a whole range of variability, even just in the process itself. So that's just something to keep in mind. We're not saying that, you know, lab data is not valid. It's just to say that you've got a lot more control over the process, so things tend to behave.
Right. And if you look at the music user manual, in Appendix E of that user manual, they actually talk about how bioretention systems are actually modeled. They do it in a fairly ambiguous way, but generally speaking, there's two components modeled. There's the treatment provided by, I guess, the detention storage above the filter media service, and that's the performance of that system is described by the universal stormwater treatment model. But as water drains through the filter media, the decay or removal of pollution is described by a lookup table. Now, that lookup table is essentially based on the lab studies that I referred to before. So, and a couple of key things to consider in relation to the way bioretention systems is modeled in music. So number one, in that music user guide, there is zero reference to any study after 2009. So whilst there might be a whole bunch of lab scale studies and field studies after 2009, they are not referenced in the music user guide. The other key thing to consider is the music user guide doesn't refer to any field study. So all of the data that music is apparently using to develop these lookup tables at least appears to be completely based on lab scale studies. And to the best of my knowledge, there's been no validation of those music results or lab scale studies in the field in any way, shape or form. So when we come to model bioretention systems in music, I really believe that it's a really long bow. Do you like my little cartoon here, Michael? I think it's a long bow to assume that bioretention systems in the field are actually appropriately modeled in music, recognizing that music is using data only up until 2009 and is only based on lab scale studies. Right, let's jump straight into the field studies. I think even you're stunned with that, Michael. You seem to be quiet all of a sudden.
Oh, mate. Look, yeah. One of those things, Brad. You know, the industry's held to completing field studies. We do a lot of lab studies, and that they are important, but there doesn't seem to be much room for error going from the lab to the field. So I think there should be potentially some sort of consideration for that fact.
You think, yeah. And look, let's dive into the field studies. This is where the rubber hits the road. And again, I'm going to separate the field scale studies into both studies of conventional bioretention system and Filtera bioretention system. But it's also worth noting that when I talk about conventional bioretention system, the standards around what is a conventional bioretention system have significantly varied over time, and they do change depending on where you are on the planet as well. And it's worthwhile noting that I guess the specifications of field scale systems that have been monitored may not be representative of current recommended best practice in Australia. So whilst I'll look at the studies, it's worthwhile noting that they may not actually be representative of what we would consider best practice bioretention systems now. And look, there are actually quite a few field studies on conventional bioretention systems, probably about 13 or 14 that I've seen. If I've missed any, please, I'd love it if people would let me know. And I've provided the full references for people and again, you can access these webinar slides after the presentation on our Ocean Protect website. But these are the studies that I've found. So let's talk about, I guess I'm basically going to go in chronological order, so oldest to most recent. So 2005, Birch, there was a study, I think they monitored 9 real events in 1999. There was a system constructed in Sydney, not sure about the construction date. It was a fairly large system of 4% of the upstream catchment. They used a filter media using a mix of zeolite and I guess sand, etc. Not sure about what planting was used, but long story short, the concentration reductions were pretty good. So TSS was about 50%. Total phosphorus concentration reduction was 51%. And they didn't see any sort of significant change in effluent concentrations for some of the heavy metals, but they did see some significant removals for some of them. They didn't have total nitrogen, but certainly TSS and TP concentration reductions were pretty good. Still short of, I guess, what we'd consider best practice targets, but still reasonably good concentration reductions. Now, this is a study in the States. There was a paper done by Bill Hunt and a few others. And if I just look at the Greensboro site now, because they actually looked at another site in North Carolina, which actually was studied several years later, and I'll talk about that later. But if I just focus on the Greensboro system, this was constructed in 2000 and 2001. There was 2 cells, both 10 square meters each, 5% of the upstream catchment. They used what they referred to as an organic sandy soil. And in cell G1, they have an internal water storage, or what we call a submerged zone. And look, long story short, and for all of these studies, I actually present the raw data, the results as depicted in the study. But long story short, they actually showed, significant water losses, which is a good thing. But we actually saw significant increases in total phosphorus and total nitrogen. So you can see the results on the right-hand side, but substantial increases in nutrient concentrations across the system. Now, a couple of things to consider is, I guess the main thing is this is a young system, so less than 1 to 2 years old. So maybe the performance might change a little bit, and I'll refer to the North Carolina system a little bit later as well. So that's just one I've studied. I'll try my best to basically charge through the others as well. And so apologies if I sort of run through these quite quickly. A paper by Davis. Was 2 systems constructed in Maryland in the States, 2 in parallel, both 26 square meters each, 2.2% upstream catchment. One used a sort of, I guess, a mix of sand and topsoil and mulch. So again, not consistent with what we'd consider best practice now. But cell B, the second cell, used an anaerobic zone, a submerged zone as well. They had 12 real events monitored in 2003, 2004, so shortly after it was built. And look, they showed TSS concentration reductions of 22 and 41%, and really good TP reductions. They didn't monitor total nitrogen. So again, reasonably good TSS and TP. TSS well short of, I guess, the targets that we'd like to see in Australia, but I'll charge on. So this is a study that a lot of people, at least in Brisbane, would be familiar with. This was done by Brisbane City Council or City Design. It was the consultancy arm of BCC back in the day. And this was a system constructed and built in Brisbane in 2006. It's shown there, 20 square meter system. They had 4 simulated rainfall events a year or 2 later. And it was basically what they refer to as a Q3 month flow discharge, dose to each system, to the system. They showed, a really good volume loss, so 23% average volume loss, and good reductions of peak flow rates, and pretty good reductions of pollutant concentration. So TSS 87%, TP 83%, and TN was 28%. So that's a pretty good sign. Still, that TN target is short of the, I guess, probably the average annual removal target, unless you consider unless you assume that this volume loss is essentially just magically lost out of the system, which again would be discharging as base flow or into the surrounding soil profile. Again, a couple of things to consider. This is a young system again, but they did have a reasonably high nitrogen concentration coming into the system as well. This is one of 3 sites that Belinda Hatt and a few others investigated. So this is the first one I'll talk about. Monash University, constructed in 2005. They monitored it 1 or 2 years later. There was 3 cells. I guess the first one would be sort of similar to what we'd consider a standard sandy loam filter media mix. Cells 2 and 3 used a different sort of mix. So I think 10% for cell 2, they had 10% vermiculite and perlite, and cell 3 used a compost and a hardwood mulch by memory, and they had planting over it as well. So probably cell 1 is probably the most representative of what we'd consider standard practice, I guess. They had data from a bunch of events, and they did show really good reductions of TSS, but phosphorus concentrations increased across all cells. So TP increased, so TP was higher in the effluent than the influent, and TN increased across cells 1 and 2 and decreased in cell 3. They did show good flow loss. There are a couple of things to consider. These are, again, young systems, and the influent concentrations were quite low, and there was a fairly high concentration of dissolved nitrogen, which is, it's harder to remove dissolved nitrogen relative to particulate nitrogen. So again, I'm sort of pointing out sort of these aspects of the monitoring and the systems to sort of show that, you know, it might not actually be completely representative of what we might consider typical and best practice, but again, the results are what they are. We're seeing nutrient concentrations increase across at least cells 1 and 2. And we look at the second site. This is again in Brisbane, constructed in 2006. And I know actually a few of the people online today were involved in the construction, so shout out. I think Charlotte and Nick are online. And look, they looked at four simulated rainfall events, and they showed, substantial reductions of solids and phosphorus and ammonia, et cetera, and heavy metals. But they do say that, and I'll quote them here, TN and NOx effluent concentrations were largely equal to or greater than influent concentrations. Again, a problem with this system, it is a young system that's being monitored. So just keep that in mind as well. This really surprised me. This is one I've been talking about for a long time, and people in Brisbane would be familiar with this one. This is Hoyland Street at Bracken Ridge, a fantastic looking system, great Melaleuca tree coverage, and really cool Lamandra understory coverage. And this was constructed in 2001, and they essentially monitored it 4 or 5 years later, and they had data for 9 real events. Long story short, they showed reductions in phosphorus and ammonia and heavy metals, but no significant reductions in total suspended solids, TN or NOx. Again, considering that they did actually have fairly low influent concentrations, but again, the results are what they are. No significant reductions in TSS and TN, but still good reductions for phosphorus and heavy metals. Now, this system, you could almost exclude this system, but I have included it because a lot of people are aware of it, at least in Queensland. This is the subject of Nat Parker's thesis a few years ago now, but it was a focus of a paper by Isri Mangaka as well. And it's basically the same system though, but a key thing to consider is, it's on the Gold Coast at Criminal Waters. But a couple of things. Number one, from what I understand, the organic matter content of the filter media was quite high, so 10%, we think, and it hasn't been established. So the geotextile, topsoil and turf are still over the top of the filter media to protect it, essentially. But look, this still was studied, and the results are still nevertheless, I guess, interesting. So Nat Parker's thesis, he had data for something like, I can't remember how many, it was quite a few events. I think you can see them there. Quite a fair bit of water was being bypassed from the system or overflowing. But long story short, the TSS concentration reduction was reasonably high, 45%. But nutrient concentrations actually increased slightly across the system. So TN increased by 13%, TP increased by 3%. So fairly small, but certainly no significant reductions. But again, keep in mind that system hasn't been established, and the media does have a high organic matter content, higher than what we'd probably recommend nowadays. But again, the results are what they are. And again, same system studied by Isri Mangaka. They had data from 12 events. And again, TSS was reasonably okay, 34% concentration reduction. TP, a slight reduction, and total nitrogen actually increased across the system by around 37%. But yeah, again, still that system hasn't been established as yet. Now, this system, people in Queensland or Brisbane would be familiar with. This was, it's a fantastic looking system. It's a system at Tilly Road, Wakeley. It was constructed in 2007, and they monitored it 2 and 3 years later. There was 3 cells in parallel with the said basin upstream. So I think the first basin, I think basins 1 and 2 had, I guess all basins had standard filter media, what we'd call sandy loam, and cell 3 had a saturated zone. And they use a variety of species. You can see the picture there from courtesy of Jack. So shout out to Jack Mullally there. And they had a stack of data. So 53 to 74 events across the 3 systems. And so what did the results show? Yeah, look, reasonably good TSS concentration reductions across cells 1, 2, and 3. Still well short of, I guess, the 80% or thereabouts targets. Phosphorus reduction was achieved, well short of, I guess, the 60 to 65% target, but still a slight reduction there, which is good. And for cells 1 and 2, nitrogen TN concentrations actually increased, and the submerged zone, the cell with the submerged zone showed some decrease in TN. Again, short of the 45% target, but still pretty good. Again, keep in mind that we did see reasonably low influent concentrations coming into the system, potentially due, at least partly due to the said basin being upstream. So you can imagine I'm doing this investigation thinking, when am I going to see a system that actually achieves 80, 60, 45 or thereabouts? So I kept on digging. So this is a study by Terry Lukey, and he's done 2 papers on this. This is a system constructed in Caloundra, 3 different systems, and they had 12 simulated storm events using, I guess, 4 different batches of pollution concentration. So, and I guess one being batch A being no pollution, so clean water, batch B being water with concentrations of TSS, TP, TN typical of urban stormwater, and C with 2 times those typical values, and D, batch D with 5 times those typical values. And look, long story short, here are the results here, and probably the most relevant to, I guess, for our purposes are the results for typical storm flow or storm flow concentrations. Again, outflow volumes are really good. But TSS and TN concentration reductions were fairly low. You can see the results there. TP reductions were really high, which is a great thing, but TSS and TN were quite low. And one of the interesting comments coming out of Terry's paper, and I'm quoting him here, so I'm pretty confident I'm not taking him out of context, and Terry says, the results of this study suggest that the long-term pollution removal performance of these systems may not be as effective as previously thought, and further research is needed. And I think that's a reasonably accurate conclusion or statement. This is a study that actually myself and Paul Dabowski and Lucy Paljo were involved with a few years ago. And I think Jack Mullally and Daniel Robson were also involved. So shout out to all those guys. But we looked at 4 streetscape bioretention systems, all in great nick. They were all constructed in 2013, and we dosed them, I think, 1 or 2 years, 2 years after they were established. And we had essentially 2 simulated rainfall events across each of the 4 systems. It was a reasonably small volume of water, which is worth noting. But long story short, we did see really good flow attenuation and flow reduction, again, recognizing that was a small volume of water that we did dose. But TSS concentration reductions, 91%, TP 83%, and TN was 33%, which I believe is the highest I've seen out of any of the studies to date, recognizing that it was still a small event and it's only simulated rainfall or simulated storm event, but still really good concentration reductions across the systems. Now, this is a study, again, from the States, and I referred to the Chapel Hill site before, which was I referred to in Bill Hunt's paper. But long story short, this is a system in North Carolina, constructed in 2001. And they use a sandy loam media, 1.2 meters deep, with a bunch of grasses. You can see, and trees and shrubs, and you can see the systems, the photos there. And this was actually monitored twice. That's a really interesting. This is a really interesting study. They monitored it first time around, 1 or 2 years after it was established or constructed. And the second monitoring was done several years later, was that, say, 15, 16 years after it was actually built. And they had data for 10 events for the first monitoring batch and 18 for the second monitoring batch. What did they show? Interestingly, they actually showed nutrient concentrations increased across the system for the first time they monitored, but when they did it the second time around, nutrient concentrations decreased. So this indicates that bioretention systems may actually improve their stormwater treatment performance over time. Now, it's not a sweeping conclusion that we can make based on just this one study, but it certainly provides some evidence to indicate that bioretention systems might actually, their performance might actually increase slightly over time. And to quote the paper, they say here, and you can see the statement here, if designed, built and maintained correctly, bioretention appears to provide sustained treatment of stormwater runoff for nitrogen and phosphorus for nearly 2 decades and likely longer. And that's a really interesting statement based on this investigation. It's probably something I actually agree with based on what I've seen so far. Now, they're all the conventional bioretention system field studies. I'm going to talk about the high flow bioretention field studies now, and there's 3 of them, and their references are there, and I'll go through each of them very quickly now. So there was Smolek, which was, when was that? That was published in the Journal of Environmental Engineering back in 2018. This is a study, excuse me, of a system it's a tree pit system, Filtera tree pit system. You can see the picture there. North Carolina. This system, high flow bioretention systems are smaller. So generally they're 0.3% of the upstream catchment. This was 0.22% of the upstream catchment. It used a Filtera filter media, and you can see the tree species there. It was a crepe myrtle. And they have a stack of data. So they monitored it for 1 or 2 years after it was activated. And they've got data for 34 real events. And long story short, and you can see the data there on the right-hand side, concentration reductions were really high. So TSS 92%, TP 54%, TN 33%. They did show significant flow attenuation, and there was some observed or unaccounted for volumetric loss as well, which we suspect might be a combination of evapotranspiration or a little bit of leakage. Who knows? Michael talked about that a little bit before. But yeah, this is a lot of data here for one system and really good pollutant concentration removals. Similarly, there was a study done by Herrera Environmental Consultants of a system in a similar tree pit system in Bellingham, Washington, in the States. This was installed in 2007, and they monitored it 6 years later. So it's, I guess, well established by now. And they had data for 22 real events. Long story short, TSS concentration reductions are 90% and phosphorus concentration reductions really high at 73% as well. A more recent study, which a few people who have tuned into our webinars before would be familiar with, because we've talked about this a couple of times. This is a study of a tree pit system in Western Sydney, treating stormwater runoff from a car park in the university car park. So this is activated in 2018. It's a system sized at 0.3% of the upstream catchment. You can see the tree there. It's a lily pilly. And this to date has been monitored from 2018 to current day. And at last count, we've got data for 28 real events. And 17 of those events were after the first years of operation, or what we call post-establishment data. So we've got, for this one system to date, where we've got 17 qualifying events after the first year of establishment. And look, obviously it looks good, but, and the results we've talked about before, we've shown, again, high pollutant concentration reductions. And interestingly, again, consistent with the Johnson study in the States, is that the system seems to be working better after that establishment period. So after that establishment period, we're getting concentration reductions of TSS 80%, TP 83%, and TN 49%. Cool. So look, this is, I guess, a summary of the studies, and I've actually erred away from providing a summary table or graph comparing all these studies, because there are, as I've sort of touched on, there's so many little intricate differences between each of the studies in terms of the filter media spec and the climate conditions, and I guess fundamentally, particularly for the conventional bioretention systems, I'm sure their sampling methodologies aren't consistent as well. But long story short, based on the results to date, these are, I guess, the conclusions that I've probably sort of made. Look, so in terms of conventional bioretention, yeah, typically we see high TSS, TP, and heavy metal concentration reductions. The TN concentration reductions are variable. And it's worthwhile noting that no field study has shown, at least to my knowledge and to date, has shown any conventional bioretention system with a TN concentration reduction of above 33%. So that's it's worthwhile noting that's water that's draining through the filter media. Obviously, we also have water that sort of spills over the system, you know, in excess of its sort of hydraulic conductivity or capacity. So we do see a lot of bypass of flows or overflow of flows coming into conventional bioretention systems, and they obviously don't get the good degree of treatment that water that drains through the filter media gets. So, yeah, it's interesting that the highest concentration reduction I've seen in any study is a concentration reduction of 33%, particularly when we're sort of trying to aspire to a 45% load reduction target. But I guess a key point I'd make is that there's probably no field study to date that for real events with currently recommended bioretention specifications in Australia. So that's a key point. It's hard to sort of, I guess, come to any conclusion around whether conventional bio works based on data, because the standards of systems that have been monitored to date really aren't that consistent with what would consider best practice standards now. In terms of the high flow bioretention systems, yeah, look, the results are fairly consistent, you know, really good high reductions of TSS, TP and TN. And I guess probably a key thing to consider is probably we are using fairly consistent monitoring techniques as well for these systems, but it is a very tightly controlled specification as well for Filtera bioretention systems. We've talked about this before, but it's a very specifically developed system that probably significantly decreases any performance variability that we might otherwise see as we might observe in conventional bioretention systems. But yeah, but a couple of general statements as well. Probably, I think it's fair to say that treatment performance is likely to improve over time, provided the system is appropriately maintained. And whilst I focused on pollutant concentration reductions, yeah, look, we are seeing significant exfiltration of flow out of these bioretention systems, whether they be to groundwater and base flow, which we talked about at the start as well.
Yeah.
So,
and Brad, just to touch onto that, sorry, I think that, you know, it's not surprising that the high flow bioretention is relatively consistent in the context of field testing. You know, it's a as you touched on, extremely tight QA/QC process and specification for Filtera. Number one. Number two, the testing methods themselves are all relatively consistent, using similar equipment and methodologies. So you would expect a tighter banding of that occurring with a high flow biofiltration. The conventional bio, really, how many checks are actually going on to the specification of the media that gets installed in the context of systems that we see in the field? Number two, there's also an extreme variability in how the performance of these systems were measured across the studies. So, you know, I think just to be fair with that point, there's a lot of variability around the bioretention system, whether how it's built, how it's made, and how it's tested versus what we see with the high flow bioretention, which could explain some difference in the results.
And look, we've talked about this online poll, and I think actually people can actually see the results themselves. And if you haven't filled out this poll question yet, I'm just looking at the results now. So the first question we asked is, do you believe that bioretention systems typically provide sustained effective stormwater treatment consistent with the design intent? The results so far, and I think you can probably see this as well as I can, Michael, and I think the attendees can do the same. So 43% of people have said yes to question one. 26% have said no, and 31% are unsure to that question number one, and that's really interesting. There was a second question. I'm just trying to scroll down to it myself, if I can. Second question was, do you believe, and again, I would really encourage you, if you haven't already filled out that question there, please do so, because it's, from my perspective, really interesting, and we'll look to share the results when we come to, I guess, put out the webinar slides, etc. But second question is, do you believe that music provides an appropriate method to predict the stormwater treatment performance of a bioretention system? And really interesting, you know, similar results. So 41, I can see the numbers changing as I'm speaking, but I think 41% have said yes, 22% have said no, and 37% have said unsure. Yeah, so interesting results. What our thoughts are essentially this, and Michael, I don't want to take you out of context because obviously we've talked about this ad nauseum, but these are our general thoughts. So we still maintain that if designed, installed and established and maintained correctly, bioretention systems provide an appropriately sustained treatment of stormwater runoff for nearly 2 decades and likely longer. Now, obviously, the caveat to that is that is a big if. We do see potentially errors being made, but again, if systems are appropriately put in the ground and established and maintained, they should provide an appropriate stormwater treatment function for several years. Will they meet the pollutant load reduction targets that are kicked around the country? That's difficult to say. I think, again, Michael, I'm keen to get your thoughts, but I think they probably should, if they're appropriately designed and installed and maintained. What are your thoughts on this?
Yeah, look, it's a big if. I think design, installed, established. I even think the raw materials constructed, are they sourced correctly? There's a lot that goes into it, and it doesn't take much to break down the process of supplying bioretention to have a system that, as we've seen from the data, can produce highly variable results. Should it meet the appropriate objectives? Yeah, I think it should. And in addition to this, as long as it's sized correctly, we have a plethora of small systems out there that, we test at 2, 3, 5%, and then we go and install at 1%. We need to really consider, are they appropriately designed, sized, then are they manufactured correctly, installed correctly, and established? And again, and we've seen it ourselves, shorter term performance tends to be lower for bioretention. Longer term performance tends to be higher. Why? There's a lot of activity into storm. These plants are growing, sucking up nutrients out of the media matrix. You need time for that plant to establish and take off, and effectively provide the accurate or reasonable long-term removal of the nutrients. It's a living system we're dealing with. It's not just a cartridge filter or a media layer like a sand filter. It's a living system. It will change. There's a lot of activity happening between the storms.
Obviously, a number of people have I hope we haven't put too much doubt in anyone's mind, but I guess we've presented a whole bunch of data. We've shown what the results show, I guess. But I guess, so now what are we supposed to do? So there's a lack of data proving that bioretention systems work in the field. Like, again, the highest TN removal concentration reduction we've seen is 33%. So what are we supposed to do now? These are our recommendations. So first up, don't believe anything we've just told you. Do your own review of bioretention system performance monitoring. And if it's getting a bit too complicated, seek advice from someone who is suitably qualified in this area. So we've certainly come to our own conclusion, but you're certainly welcome to do your own research and come to your own. The advice is still, second point is, our advice that we've been talking about for donkey's years is the same. Making sure it is critical to ensure that any system is appropriately designed, installed, established, and maintained to at least augment and I guess maximize the stormwater treatment function of this asset. And another thing to consider is that we'd really recommend others consider undertaking appropriate real-world long-term performance monitoring. Now, I recognise that's beyond the scope of 99% of people probably tuning in, but and we're actually really pleased to see that Blacktown City Council are again leading the way in this regard. So Blacktown City Council are actually have commissioned a group to undertake essentially what they refer to as this water quality and quantity data acquisition project, which is basically a 5-year stormwater treatment performance evaluation of 2 GPTs and also 6 bioretention systems. So again, Blacktown City Council have been leading the way in various aspects of water sensitive design. So it's really great to see them essentially doing it again and actually undertaking some appropriate long-term performance monitoring of bioretention systems in this regard.
Yeah, and look, I think, Brad, I think they're ahead of the curve in this situation. We completed this literature review over the last month. We determined where the systems and what the performance of bioretention was. We've effectively identified bioretention can work, but we probably need to tighten up the specifications and the checking to ensure that what we design is what we're getting in the field. And the other side of the coin, there needs to be, some more thorough testing of systems from a, initial period and also over a longer term after establishment. So I think Council was a bit ahead of the game here and probably recognised this fact and look, good on them for looking into the data more closely and providing some of the answers for bioretention requirements.
Hey, look, and people might be pleased to know that's actually the end of our presentation. But I see, Michael, there is a stack of questions coming through and I think comments as well. So just a reminder, if you do have questions, please put them through. But obviously, I think a fair few people have already done so. And look, we'll try our best. We're sitting at what's 45 minutes to date. We're going to try our best to get through all of these questions. We recognise that everyone probably needs to get back to work, but I think we'll essentially basically try to address as many questions as we can in the next 10, 15 minutes. And if people really want to stick around for longer, they're welcome to, because we'll essentially try and go through each of these questions now. You ready, Michael?
Fire away, Brad.
Righto. Let me just give me a sec. I'll close down. Where are we? Hang on. Where is it? I'm just going to flip this around. So I'm just going to close down so I'm just going to go to the poll. Again, the poll questions the responses haven't really changed that much, but I'm just going to go, gee whiz, we've got 16 questions and 22 comments in the Q&A in the chat as well. So, oh man.
Off the top of the questions, Brad. Start right at the top.
Okay, I'm going to start right at the top. A question from Irian Crab. Green Star requirements for hydrocarbon and free oil. How effective is bioretention without music modelling?
Look, I think it is effective. There's no doubt about it. I think from what I've seen with field testing different systems, the load of the oil and grease and hydrocarbons will actually affect the longevity of the film media itself, because it tends to blind. So I think it is effective. Again, depending on inflow concentrations, depending on how effective it will be, I think it'll provide a good treatment function, but I'd be concerned about the longevity if there were sustained high loads.
Question from Zorek. I'll just say Zorek. What causes an increase in TM, Michael?
Wow. Look, low concentrations tends to be a bit of the devil with these systems, or any system really. Remember, you've got a living plant. You've got organic material within the media. If you choose the wrong type of organic material, or you overdose the filter media with a higher proportion of organic material, you're going to leach N and P out of the system. If you have die-off of your plant, you will leach N and P out of your system. These things tend to cause a release of nutrients, together with low influent concentrations, which the device is probably not really designed to handle. These things will increase TN coming out of any bioretention or filter type system.
We've got a couple of questions from Andrew Thomas. He's never short of an opinion, and he's an avid tuner in of these webinars. But I think actually we've addressed your questions already, Andrew. So correct me if I'm wrong, but I think we've actually addressed the first one and the second one in terms of, the second question is, how confident should we be about the value of bioretention systems? I still maintain that bioretention systems should provide an appropriate stormwater treatment function, so that their value is significant. I don't want to discount that at all. So again, but we just, from my mind, as you sort of referred to in the first and second question, is that we probably do need to actually go about and appropriately demonstrate that performance as well through proper real world system monitoring over a long term.
Yeah, and look, more checks and balances in how we make it and deliver it, no doubt, so we can get tighter. Guarantee we're tighter to the specification that we're looking at, and appropriate monitoring of the devices. They're the two key things. It does work, but again, I think a bit more control, it can work a lot better.
Yeah, Ruby from Northern Beaches Council has said, concerned about the contribution to groundwater and base flow is being dismissed. This is exceptionally important as development has contributed to a significant lowering of base flow in creeks, and the alternative is the water drains for the pipe system and can contribute erosion of waterways. Also in areas like mine, we are trying to maintain the water balance in coastal aquifers and prevent saltwater infiltration. So maintaining groundwater is essential. Yeah, look, first up, I don't believe that we should just assume that any water that is lost to groundwater is just magically disappeared, because certainly the groundwater and the base flow is definitely still a receiving environment. But I still maintain that if we can promote the exfiltration and infiltration of water into the soil profile, it is a good thing. But again, we still need to make sure that pollutant load isn't just being essentially just ignored and not accounted for appropriately. Ruby also asked a second question. As probably one for you, Michael, has there been any study that looked at the risk of pollutant output from a biobasin that hasn't been maintained compared to a proprietary filter device that hasn't been maintained or replaced? She says, I suspect that biobasins still provide some degree of treatment when neglected.
Look, I haven't seen these studies, more or less myself. The issue that you will find, though, if you don't maintain anything, is it won't treat any flow. That's more or less your problem. So will they provide some degree of treatment? Yes, but it'll be negligible if you can't get any flow through it. A lot of filters, whether it be bioretention, sand filters, cartridge filters, you know, the biggest issue would be failure on the surface of the media through to solids like clay, silts, things like that, building up on the surface and forming permeable barrier and stopping flow going through the system. So I think if you neglect any system, there won't be really any type of stormwater treatment function. You know, you just can't get the water through it. All filters block that way, and you know that's more or less one of the mechanisms. Base flow is another concern with anything bioretention system that has organic material in there. If you consistently make it wet, you know, you'll basically get some biofilm building up and blocking the flow down in deeper layers within the media itself. We've seen that as well. So, you know, appropriate maintenance of any device, you know, is ultimately required to ensure they provide some stormwater treatment function.
Now, Mika Zeshki, apologies if I mispronounced your name, they make 2 points. Basins, he says, basins improve as plant root network establishes. We have tested this. Yep, we agree. Yep. It obviously, we think the results indicate that bioretention pollution removal increases marginally over time, but also there's obviously a bunch of studies that show the plant roots are really important to maintain that hydraulic conductivity. And Mika also says, we used to talk about residence time for the polluted water to be absorbed, treated. I believe we should be looking at a slower release mechanism for better results and also aid in the plant survivability. What are your thoughts? Yeah. I'm not sure if it's that simple. Certainly, like obviously the Filtera bioretention systems, whilst water does drain through the system reasonably quickly, the water is still actually, a lot of the water is actually retained within the filter media, particularly because of the presence of that mulch layer. So I don't think it's actually as simple as sort of saying, oh yeah, with slower release is just generally going to be better for plant livability. We obviously see a lot of bioretention systems getting blocked, the filter media being blinded and the water ponding for an extended period and then subsequently the plant's dying. So I'm not sure if that's I'm not sure if Michael, have you had any further thoughts on that?
Yeah, look, I don't, you know, there's enough contact time. If you think of the processes happening intra-storm with a bioretention system, you know, you've got obviously physical filtration, you've got cation exchange, absorption, things like that going on within the media. They're relatively short, quick reactions that take place and happen quite frequently and quickly. A lot of the interstorm activity, though, and we're not talking about, you know, residence time. It's really just about time for the roots to actually just soak up those nutrients from the media around the rhizosphere and plant. So, yeah, I don't think the extra residence time is really going to provide much further, I suppose, performance during the storm. That's tend to what we see when we look at these systems. But definitely that time between the storms is when, and we've measured different depths with high flow bioretention, different depths of NMP content from the top surface, the middle and the bottom. And it's interesting to see how that changes during, you know, if you look at your antecedent conditions and also, you know, seasonal changes as well. So, you know, well, I don't think we need much more residence time. And as Brad pointed to, you know, using a mulch layer can stop your weeds growing. It can basically stop all the sediment getting into your media, which will block it, and also keep moisture in the media for longer so that plants can survive these prolonged dry periods.
All right, we're going to have to keep some of these answers a bit shorter, Michael. You know, I know how you love talking, but we've got a lot of questions to go through. So Brett Phillips says, obvious comment, you're comparing systems at different scales lab columns versus tree pits versus large scale systems. Performance of a tree pit is not necessarily a guide to a far larger real world system unless you believe the performance is scale independent. That's a really good point. Yeah, like I've made the point before about we're transitioning this lab scale data to field scale systems, which are often massive, like they're 2,000 square meters plus type thing. And I think that's a real stretch, particularly when you consider the hydraulics over a large scale system are very different, particularly with a standard inlet configuration for a conventional bioretention, in that water comes in at the end and you might have your outlet, 50 meters plus downstream. That's no representation of the lab scale study. Certainly for the Filtration systems, the monitoring we've done on the real world systems, recognizing that our tree pit, I think it's probably a reasonable assumption to make in that these systems would be reasonably representative of a much larger Filtration system, only because for the Filtration systems, we very much maximize flow distribution. So for people who are familiar with the larger bioscape systems, we do have a whole bunch of bubble up pipes to ensure essentially that flow is appropriately distributed across the system. You don't see that in conventional bioretention systems, or at least rarely. So yeah, that's Michael. I dare to say, have you got any further comments on that?
Look, yeah, I think you would need to. I think you need to test both. The good thing about tree pits is there's a lot more control over measurement of flow, also water quality. Remember, if you're getting a large system, it's extremely difficult to pair your influent and effluent samples. So therefore, how do you really work out, with a higher level of certainty that the results are actually accurate or valid? It creates a lot more issues. So, but agreed, there would be differences in performance with scale potentially, and that should be measured. And congrats to Blacktown Council, they're looking at testing some big systems there as well. So, I think we'll see that data come out in a couple of years, Brett.
So if I just pause here for one moment, so that's an hour we've taken up for people's time. So if you have enjoyed this webinar, thank you so much for coming along and attending. If you'd like to see more comments, or sorry, more topics or different topics or whatever you want, obviously these webinars are very popular. Let us know what you want us to talk about. But certainly thank you for everyone who's still dialed in. I'm actually, myself and Michael are going to stay on the line though, and actually address each of these questions now. So if you don't want to do that, and you want to go back to work or whatever you want to do, that's cool. We'll actually include the recording of these answers in the YouTube video that we'll have on this webinar as well. But look, if you want to stick around, that's great. There's still 250 people dialed in, so which is a great sign. And the first question, Michael, I'm not sure if you've seen it, is from the godfather of stormwater. We're very privileged to have James Lenhart dialing in. So James is dialing in.
America, better make sure it's right, Brad.
So you better get this. You better get this right, James. Sorry, Michael, because James has asked you a question. Yes, you do. So greetings, James. And James asks, do any of these studies monitor the bioretention infiltration rates to establish if they remain at or above design?
Look, potentially not. There's limited, as we know, with maintenance. There's limited representation of, the long-term flow rate of these devices. We know with high flow bioretention Filtera, we do, and we appropriately test. So we would do, probably a saturated hydroconductivity test, both dry and wet. We would run, across a basin of, say, 100 square meters, we might run 4 or 5, or probably 4 representative samples. So we know we do on our side, but I think generally for bioretention, when people look at maintenance, absolutely not. I don't see that data out there really.
Yeah, I think I've only seen a couple of studies. I think one was done by the COC for water sensitive cities, because I remember they made a conclusion around that. Yeah, the presence of trees and other sort of, I guess, plants with a high root biomass does maintain hydraulic conductivity. So I think that's one study I can remember. The second one is actually one I know one of my colleagues, Nicole Romillo, authored many years ago. She looked at a bunch of bioretention systems in the Noosa Civic Shopping Centre. And I'm sure that paper is available. And by memory, the hydraulic conductivity changed a little bit, and it was variable. So I think sometimes the infiltration rate was, I guess, maintained or increased, but some systems actually did show a decrease as well. But don't quote me, I'm sure those papers are out there. So I'll charge on to the next question. So Justin Sweet, have studies been done with more mature trees installed with the systems opposed to immature trees?
Hard to say. I think that one, again, we're delving right in the detail of where bioretention is. I think we haven't even answered, or guaranteed in some cases with the field testing on the exact specification that the entire media is made to before you even install it and put a plant at a certain age. Will a mature tree or a tree that's growing versus not provide different performance? I think absolutely. Yeah, definitely. I think there will be a difference, but I don't know of any studies, Brad.
No. I can only talk to the studies that have shown us, I guess, systems with that have been in the ground for longer. Obviously, they'll have more mature trees relative to when they were first planted in, and we generally see performance increasing slightly. But yeah, hard to say. Andrew Thomas, another one of his cracking comments is Blacktown City Council awesome? He thinks so. We'll skip on. Jay Keem, what maintenance measures would best maximise maintain biotreatment effectiveness? Are there any practical solutions to promote root growth, i.e. to increase treatment? So look, first and foremost, there is guidelines available to that best practice guidelines around how to maintain bioretention systems, both conventional bioretention systems, such as the Water by Design guidelines, and Filtration bioretention systems like our maintenance manual. So that would be the best way to maintain devices and maximize performance. Follow the advice in those guidelines. In terms of practical solutions to promote root growth, yeah, look, generally appropriate maintenance would be the first one. But secondly, I guess put in or plant vegetation that does actually have a good root mass and can actually grow roots effectively and quickly. And I guess that's pretty consistent with the advice coming out of the FORB group and others, CRC for extensive cities, that they do provide a list of recommended species to promote, I guess, the action of that root growth. Michael?
And look, don't believe us. Do some research on mulch. Like if you're going to hold the moisture in the soil for longer, obviously that, with prolonged dry periods that we get, whether it be in Queensland, lower rainfall that we get in Melbourne, even though they're more frequent, or some of the rainfall, the temperate rainfall we get in Sydney, if you can hold the moisture in there, and also have a layer that stops the sediment getting out to the filter media and stops the weed growth, all you're doing is effectively prolonging the media bed within the system and helping the plant actually, grow a bit better. So yeah, we use it for several reasons, and from what we can see, it certainly provides an effective outcome.
Alan Walker has a few comments. Training of contractors to build biosystems is critical. Often builders don't understand the real purpose of environmental treatment systems, so there is a real issue. Completely agree. No objections there, Alan.
And even going back to how the bioretention media is mixed and made, taking a subsample per, 1,000 tonnes, is that appropriate for what we're trying to achieve when we're trying to hit these numbers and get a consistent product?
Yeah,
probably not. I'd say.
So it's a real leap of faith that the filter media spec is consistent with a sample taken 6 months ago, etc. I see a whole bunch of people have raising their hands as well, so I'm still trying to get through these questions. So Remy says, can you please email a list of the papers referenced at the end of this? Yes. The webinar slides will be made available on the Ocean Protect website under the education webinars, and that'll include the full list of papers. Amy St. Lawrence, regarding methods for monitoring of biofilters, in the studies you presented, are the results generally from single grab samples of inflows and outflows per event? Do you want to talk to that, Michael? Or
yeah, look, not really. A lot of them, I think, Brad, or some of them have been done with flow samples. There's a whole range of different treatment methods. That's probably one of the performance measuring methods that have been chosen. That's probably one of the issue with the high variability with results. Look, if you're going to do grab samples, great, but they're not going to give you, real confidence in how those systems are performing. Flow proportional, automatic, paired, influent and effluent monitoring of your systems is what's required, measuring rainfall, over multiple events.
And that's what's done
multiple aliquots per storm will give you a real confident idea of how those systems will perform.
And just to confirm, is that what's being done for Filtera bioretention systems?
Yes.
Yeah. So Aaron Wright. So greetings, Aaron. Nitrogen. He loves talking about nitrogen. So it doesn't surprise me, this question. Nitrogen removal seemed highly variable. and minimal in bioretention systems. Effective nitrogen removal requires aerobic and anaerobic conditions. Does best practice conventional bioretention system design need to be reconsidered to include an internal water storage amended by a carbon source to both extend retention time and encourage denitrification? So I'll talk to conventional bioretention systems first. So yeah, the conventional advice generally is actually to include an anaerobic zone, but interestingly, a lot of councils don't want this either, I guess because of concerns around costs and long-term function, maybe, I'm not sure. But also the results in the field scale environment, again, still variable, even for systems with an anaerobic zone. You'd expect an anaerobic zone internal storage zone to enhance denitrification, so subsequently enhance nitrate removal and subsequently TN removal. But yeah, I guess in terms of the advice, the best practice advice does actually vary slightly, depending on who you talk to. Michael, do you want to comment on that at all?
Look, yeah, I think probably I'd be more, you know, if you're talking about a carbon source and extended retention in the system, you've got to ask yourself, you know, how long for bacteria and bugs to become effective at providing some denitrification function, that you would have a relatively large sump, and you'd have to capture that water and effectively hold it there for a period of time. Now that could be 12, 24, 36 hours. These systems would be huge. So I think probably looking at the effectiveness of, say, a process like phytoremediation with the system, and looking at different plant species with different soil blends or media blends, could provide a useful function that's not going to blow out the size of the system. That's for sure. So I don't know if we're, at 1% of the catchment, 2% of the catchment, how do we do that? I don't see how we could effectively provide some sort of meaningful level of denitrification in such a small area.
A question from Amy St. Lawrence. So if I remember correctly, music seems to view water losses through infiltration as a bad thing. Is this correct? If so, this is a problem, as often one of the objectives of bioretention system is, in certain situation, is to recharge groundwater. Yeah, so just to clarify, infiltration out of the base or the size of a bioretention system is probably actually a good thing. The key thing, though, to consider is a lot of the guideline advice is around demonstrating compliance with average annual load removal targets, which includes discharges to the groundwater or base flow. So you can't just assume that the water is lost. But in the latest version of music, you can actually capture that lost water, the exfiltrated water, and put it back into the receiving node. So if you think exfiltration is present, yeah, please model it, but make sure you do still account for that water and associated pollutant load loss. Pollutant load being discharged to the environment. So again, it's still, exfiltration is still a good thing, provided you are appropriately treating that water. Daniel Solomon says, how effective is bioretention and Filtera systems, for that matter, in reducing mean volumetric flow through evapotranspiration or other means? So I sort of said this at the start, so you might have missed it, Daniel, but just to reiterate, yeah, so bioretention systems, we think a typical system size to meet the local pollutant load reduction targets, generally you're going to get an ET loss as predicted by music of between 2 to 5% roughly. And I think we believe music actually does provide a reasonable good prediction of that. And it's the same thing for bioretention, for Filtera bioretention systems. So where we've monitored flow volume, we've seen losses of around about 5 to 6%. And music generally provides a pretty good estimate of that when we modeled Filtera Bio using the Bio node. So both are reasonably effective at reducing that flow volume. And again, music does provide a reasonably good prediction of that loss as well. Jury Jung provides a couple of comments that corrected me on one of the things about the Mangaka study, which thanks to that jury. She says, or he or she says, plus I totally agree that the removal is based on inflow concentration. Monash's group field study also noted that the inflow concentration being low could have impacted the negative result. Yeah, so that's something we've tried to reiterate several times, in that when we often see a low pollutant concentration reduction, it seems to be at least often in part where we actually see low influent concentration. So it's obviously harder to remove pollution when that water that you're treating is actually quite low in pollution concentrations. Alternatively, it's actually easier to treat water that's really dirty as well.
Yeah, absolutely. And I think Jury, I think you've she's got a great point here. I think that the variability in these testing methods can just really throw the results out to two questions there. Influent concentration will vary the outcome significantly, and also the different methods as well will vary what we think the performance of these systems are. So standardized testing to a nice stringent protocol, with the correct equipment can reduce some of that variability. But remember, it's field monitoring. You're always going to get some variability with the systems.
Ruby asked another question. Can bioretention systems become polluters when not maintained? Good question.
Potentially. Look, any system can if the pH does drop. You can get some leaching, certainly with some metals coming out of the system. So depending on what state it is in, depending on how much flow, like if flow can't get to it, well then there's not much damage it could probably do. But if flow could get to it and the pH was low, yeah, you could have some issues there, certainly, with some leachate coming out. And again, but not even just maintaining it. If you actually design it, incorrectly and you use too much organic material, you will get a flush out of NMP coming out of the system, no doubt, for an extended period of time.
Blake Allingham asked the question, what is considered appropriate maintenance of a bioretention system? So again, there are guidelines available for conventional and Filtera bioretention systems, but generally speaking, you generally often need to have to, for conventional, it's recommended often to scrape the surface of the filter media to remove that sort of blinding of the filter media, and we've seen that in both streetscape systems and larger scale systems. Pulling weeds, replanting with vegetation, taking out litter, etc. The key maintenance intervention for Filtera bioretention system is essentially the same, but we also use a double shredded hardwood mulch layer, 75mm deep roughly, on the surface of the filter media to provide that protection of the filter media. We think it's actually a lot easier, and it is a lot easier to essentially have that mulch as a screening, providing a screening function. So the solids that could otherwise blind the filter media are appropriately trapped in that mulch layer, and we can easily and quickly and cheaply remove that and again put back new mulch. William Veramendi asks, is there any records of non-maintained bioretention systems? My view is that maintenance is not an issue because they are natural systems. To be honest, I totally disagree. All assets need maintenance. So if you leave a stormwater treatment asset, whether it's a natural system or otherwise, and you don't maintain it, its function will diminish over time. And we've seen that time and time again. Even something as simple as with, I remember Ralph Leiter talking about the streetscape systems. Water physically can't get into these systems unless you remove the buildup of sediment at the inlets. And similarly, we often see for bioretention systems, the conventional bioretention systems, that the filter media gets blinded time and time again. And that media, sorry, that buildup of sediment fines does need to be manually removed. If not, the water will pond. And the system will essentially just not, you won't get any sort of water draining through the filter media. Might still do something, maybe, but certainly its treatment function will be significantly reduced. So I think this idea of zero maintenance being required for natural systems is complete rubbish.
Yeah, look, you can look at a system and there's trees there and the trees look like they're growing and it looks great. But if you've got a cake layer of sand silt clay, that's 25, 30 millimeters thick, you're not going to be treating 80% of your runoff. You might treat a few percent at best. Sure, water will sit there on the surface, it'll stop the media drying out, it'll let the plant grow, but you won't be treating any runoff. There'll be no treatment. So the whole overall effectiveness of the system, whilst it might look okay, will be negligible from a stormwater quality perspective.
Question from Mark Ibrahim. As you noted, these systems only function with proper maintenance. Why do you see council assuming that typical residential homes can maintain a bioretention system when they can barely maintain a rain tank or roof gutters? We see rain gardens as being redundant or becoming redundant, even if they are constructed correctly, and councils need to consider Filtera systems that can be maintained by a supplier. Look, I agree. Any system you put in needs to be maintained. I've said this just before. Just as a side note, Filtera bioretention systems can be maintained by people outside of Ocean Protect. It's as I indicated before, it's a reasonably simple maintenance intervention. But look, they all need to be appropriately maintained. And if we're talking about systems in private ownership, there needs to be some sort of agreement in place. And for councils to actually do something about it, enforcing that agreement to ensure that these systems are appropriately maintained. If they are not maintained, we might as well not bother. So again, I see a lot of councils doing a really good job of actually putting in appropriate development conditions that basically mean that the developer or the site owner needs to sign a long-term maintenance agreement for the maintenance of whatever asset it might be, whether it be a underground system or a natural system. But where I see a lot of councils falling down is that they're just not enforcing those maintenance requirements, and that needs to change.
It's possible. We the councils collect bins from out the front of every single house every week. We're talking about maintaining, even in street trees, there might be 3 or 4 or 5 houses going to a street tree. We're just saying, hey, maintain with that one device in front of 3 or 4 different houses once every 6 months to a year. I think we've just got to get, we've just got to try a bit harder, I suppose, in the enforcement of it. If we say to people, hey, don't maintain it because they don't understand what it is or how it works, they won't. But if we explain the benefits, I suppose, of some of these systems, and again, we have to support council in trying to get these systems maintained. We do that. I think a lot more systems will get maintained. But it's key to the performance long term. Maintenance is key.
So one more final question, then I'm going to go to the chat tab, and I see that some of the things were addressed already. But one last question, it might be a doozy for you, Michael, from Brett Phillips. Any experience in installing biofilters in acid sulfate soils areas, coastal locations? Question mark. Avoids flow exchange with ASS.
Oh, Brett, I think that's termed as middle leg stump. No, I have no experience installing biofilters in that spot at all.
You clearly don't want to dig a hole and put a system that'll drain a groundwater and expose acid sulfate soils, basically. I'm going to go to the comments.
Unless you want to have a crack at it, Brad.
That's my comment. That's the only thing I'd say. Look, there's a lot of comments, and I thought I saw a few people raising their hand that wanted to talk. So if you wanted to raise your hand, I'll try and get to that at the end as well. But please do it again if you're still with us. Alan Walker, these are comments. Bioretention works if well conceived, designed, and constructed. Otherwise, it can be a constructed disaster that adds more headaches and solutions. Yep.
Agree.
No disagreement. Leonard Strub, in low density residential subdivision, can smart trees at a rate of 1 every 15 metres behind curb work for infill development, i.e. can smart street trees be thought of as small bioretention? Yeah, absolutely. That's a tree pit system like the ones we've sort of shown for the Filtera systems. Often see in a streetscape environment in particular, you are confined for space. So the ability to put in a conventional bio, which might be sized at 1.5, and probably should be bigger, it might be very difficult to do, but certainly with a smaller high flow system sized at say 0.3%, that's very achievable.
Yeah, and look, conflict of interest here, we obviously sell high flow bioretention, but if you're especially looking at street trees, Filtera treats 20 times the flow rate of conventional bio. You can divert more flow to each Filtera. So can you actually get enough flow, even at 1.5 to 3% of the catchment, enough flow treated by a normal bioretention system? Maybe not. But street trees, great idea. And you would feel that high flow bioretention, certainly in that specific case, does have a high advantage.
Yeah. Comment from Alan Benson. Greetings, Alan, President of Stormwater New South Wales. He says music provides an estimate on the data of bioretention systems. Many authorities utilise margins to allow for the shortcomings of the model and its supporting data. Yeah, that's great if they do. I certainly would encourage conservative designs for a lot of these systems.
Yeah, I think Alan's probably referring to this, the Norby requirements there in Water New South Wales. So, there is a little bit of flexibility, I suppose, and a little bit of overestimation in what you have to achieve, rather than just the hard and fast 45.0% term reduction that everyone sort of strives to hit in most places around the country.
Yeah, comment from Leon Rollins. The Paljo study is the only one you've mentioned that could be considered as approaching current best practice. I'm not sure if I totally agree with that, but I certainly have tried my best to highlight the fact that the filter media specs and the plantings, etc., do vary across the systems. A lot of these systems have predominantly used a sandy loam media, and often they do add organic matter, etc. And yeah, you're probably right that Lucy Paljo and Dabowski and my paper, the systems assessed were certainly probably using more contemporary standards. But I guess that's a deficiency that we've tried to highlight as well. Like I really believe there's a real need for appropriate long-term monitoring of systems using contemporary standards. So that's the point we're trying to make, in that we actually think that conventional bioretention systems should work using contemporary standards, but we'd really like to see some evidence to demonstrate that. Andrew Francis, regardless of the performance rates from field tests, do you feel that the current best practice media profile is still the best for bioretention, or should we be looking at using different filter media? I'll let you answer this first, Michael, because I have my thoughts.
Look, I don't think there's too much potentially wrong with the spec. People are going to have different views on what the spec should be. I think the elephant in the room is, well, are we actually manufacturing it to that spec if we do one QA sample 6 months ago for 1,000 or 2,000 tonnes of media? How much confidence can you put in those results? Have we appropriately mixed the organic material? Have we mixed the right type of organic material? Have we mixed a little bit in this corner over here and not over there? I think the specification's not bad. It's just, I suppose, the checks and balances in place to ensure that what we've specified is actually what we're getting in the field.
Cool. A comment from Tim Davies from Brisbane City Council. Greetings, Tim. How does synthetic stormwater versus natural dosing typically affect load reduction rates? Gee whiz, I don't think we know. Would you want to even have a guess, Michael? How would using synthetic stormwater differ to actually real world events?
Oh, look, easy speciation of N. Just play with your particulate nitrogen versus soluble nitrogen. Ramp up your particulate, drop your soluble down in your dosing.
Yeah, but how do you think the results would actually vary? Assuming that you've got a natural event using that has typical pollutant concentrations, how do you think it would actually vary compared to a synthetically dosed stormwater?
That speciation difference will give you your biggest variation, together with your influent concentration.
Yep.
You control those two things, you should see similar performance with your field studies. It shouldn't vary too much. From what we've seen and all the research that we've done and everything that we look at, those 2 points there will change the performance of any system markedly. So, as long as you get those right, those 2 points, you would expect fairly consistent results. But again, it's field testing. You get some null outcomes which you're like, whoa.
Alan Benson chimes in again, interested in what you'd recommend for a sampling regime. BMCC has installed multiple devices in a couple of catchments in the upper Blue Mountains. Sampling today has concentrated on upstream and downstream devices plus whole catchment load studies. I think Michael, this might be a conversation you need to have offline with Alan, because you can talk about appropriate sampling regimes till the cows come home.
I could bore everyone to sleep, but I won't.
We'll charge on.
Look,
Alan,
look, bottom line, a good protocol, with appropriate checks and balances using automated sampling equipment, set up by guys who actually know what they're doing and how these systems work. That's and how this gear works. There's a lot of experts that say, oh, we know how to monitor, and then, there's a lot of variation you can get with the method. I can simply just get an auto sampler, turn one tube around one way, another suction tube around the other way, and get different results for a pit. We can show a pit that gets 10-20% solids reduction pretty easily with this equipment. So the right equipment set up the right way, I think is paramount. And again, a good protocol, but with appropriate checks and balances in there.
Alan Walker chimes in with a few more comments. Yeah, music results are questionable. Filter media use often questionable. Systems often built too low for the system to be effective. Often overflow options not considered. Andrew Thomas, Blacktown City Council, are awesome. Thank you, Andrew. Comments, thanks for that. Very informative and worthwhile. Thank you. Informative. Shayla asks, who are the manufacturers of the Filtera bioretention system, or is it generic type? We actually just disclosed at the start of the webinar, which you might have missed, Shayla, but Ocean Protect are the manufacturers within Australia of Filtera bioretention systems. So, yep. There's a few comments to Michael. Tim Davies, would be great to know the ultimate concentration to see how close they are to local water quality concentration targets. This is the ultimate goal after all. Removal percentages can be misleading based on inflow concentration. Yeah, totally agree. I'd personally like to see some sort of effluent concentration target and some sort of, I guess, hydrologic effectiveness assessment for bioretention systems as well. I think relying solely on pollutant load reduction targets is probably a bit too simple and obviously impossible to demonstrate compliance with as well.
Yeah, look, agree with that, and you don't have to look too far. Washington State Department of Ecology, North America, obviously high concentrations, high percent reductions. They have a couple of different measures where they say, look, if your concentrations are over this magnitude coming in, percent reduction, below this point here, because we know that percentage reductions drop as the influent concentrations drop, they have an effluent target. Perfect. That's exactly what we should be having.
Andrew, I think Sparrons, some councils due to lack of, some councils due to many reasons, e.g. lack of funding, can find maintenance of bioretention systems problematic. Especially for new development, councils prefer a treatment train approach, not just rely on one device. Unfortunately, this approach is often not attractive for developers. Sure, yep, I agree. But whatever treatment device or treatment devices you use, the concept and the advice is still the same. Each element of any sort of treatment strategy needs to be appropriately constructed, designed, maintained, etc. But obviously, when you sort of have multiple devices, you have less of your eggs in the one basket, I guess. Mark says, Trout says, is not a simple case of chambers for greenfield or in, Mark, this is a question. Is it not a simple case of chambers for greenfield or in flood zoned and bios in greenfield? Don't know. That's prescriptive, maybe. It's an idea, Michael. I don't know.
Water system ever design the most appropriate technology for the land use and the pollutants.
And the constraints as well.
Yeah, constraints. Like, we should be, high density sites, industrial, commercial. I think, cartridge filters are more appropriate, especially when you have, detention tanks and things like that. So you integrate greenfield sites. Yeah, bioretention. If your loads are a little bit lower and you've got a little bit more space and you can integrate bioretention or high flow bioretention appropriately, why not? I don't think it's just going to be one size for one technology fits all.
Comment from Ben Peneleric, #PlantPower, Ben. So it's important to point out that music is only intended, I'm just quoting Ben here, important to point out that music is only intended to provide a conceptualization of the average performance of a bioretention system over a year, depending on climate. It's a conceptualization only, not evidence of performance over the asset life cycle. Critically, if we are to have confidence that bioretention is working, then we need to monitor, 1, performance over their life cycle. This is long-term. And 2, the relationship between design, construction and maintenance with performance. In addition to this, it's important that the targets we have set for them are actually delivering the outcome that we want, which is protection of waterway health. Thus, in addition to the monitoring described above, we need to monitor waterway health and its relationship with bioretention performance. Totally agree with you, Ben. I'm sure Michael doesn't either. And Ben goes on to say, monitoring is both costly and resource intensive, but were we to get together as an industry to sponsor a long-term longitudinal monitoring project at select sites across the country, we would reduce the costs through sharing and share all the benefits. Totally agree, Ben. Well said. Alan Walker, another comment, lack of preparedness to budget for maintenance of biosystem is often a major cause, particularly as auditors do not regard environmental systems as capitalizable infrastructure and hence not depreciable. Completely agree, Alan, and I think everyone else is just sort of saying thanks, very informative. Alan Benson says you're biased, Michael. I agree. Nigel Bosworth, this may have been covered before, but how do we use high flow bioretention media in music to the satisfaction of councils? This varies. So depending on where you are in the council in Australia, The advice is to either use the bioretention node, modelled in accordance with the recommendations in one of our reports, and I can flick you that to you, Nigel. But long story short, model is the bioretention node, but change the T and ortho P concentrations of the filter media and the filter media depth and hydraulic conductivity, etc. And we've actually compared the music results with real world monitoring results, and actually do provide a reasonable comparison. But some councils, specifically Blacktown Council, recommend the use of a detention node and generic treatment node to model the performance of bioretention systems. Sorry, monitor the performance of Filtera bioretention systems, which is fine. Yeah, thanks.
I suppose in short, you're in Australia, contact Ocean Protect. North America, contact Energy Solutions. That'd be the two guys you go to. So.
Yeah, Trout asked a couple of questions. Does a heavily weeded bio indicate health? It's a good question. Often a whole bunch of weeds can actually probably indicate a system that actually is at least performing a good stormwater treatment function, depending on, I guess, where the water is ponding and the system is actually draining appropriately. So weeds pull up nutrients just as effective as plants that are recommended, but they may be an indicator of poor health, i.e. Extended ponding, for example.
They tend to, from all the monitoring that we've done and the maintenance that we do, and we do a lot of maintenance of these types of systems, high flow bioretention. We also maintain standard bioretention plus cartridge filters. Weed growth usually results, and we tend to see a lot of it in sediment deposition. So, okay, it might look okay, the system, you look at the weeds close and there's a lot of weeds that looks a bit ugly, but typically you'll find that there'll be a sediment layer where the weeds will grow. So your hydraulic function will be significantly impacted. So you might look okay, but it actually won't be getting much flow through the system, especially where those weeds are.
Cool. One last question from Trout. And I'm keen to get your thoughts on this one, Michael. What is the rule of thumb in terms of percentage of catchment for residential, commercial, car park, industrial developments? How big should a bioretention be as a percentage of the catchment size? And how does this advice compare state to state and conventional versus bioretention, Filtera bioretention systems?
Well,
this is a great question. This is the best question saved to last, I reckon.
Oh yeah. Look, I think if you look at Filtera high flow bioretention, we've tested that and recommend a minimum size of 0.3%. Like, it's tested at that limit. That's the minimum size. Systems will be 0.4, 0.5, 0.6%. Granted, in some applications you will need a bigger system, but we've tested it right at the lower edge, right at that bottom limit. I suppose the question probably back to Brad for this one, for the normal bioretention, if we're not testing at 1%, should we really be sizing these systems at 1%? Like we see in North America, we see systems are not 1% of the catchment. They're like 4 to 5%. So, we've got it all the way down to the smallest possible size, and yet we haven't done much monitoring of that size. Is it really appropriate?
This could be a whole webinar in itself. How big should a bioretention system be? Look, if you look at music, you can achieve the SPP targets or whatever the local pollutant load reduction targets are with bioretention systems ranging from 1.2, 1.3 to 0.4%. That's a conventional bioretention system, which I find staggering in hindsight, really having looked at this data. When you look at the lab scale data in particular, in that all of the hydraulic loading rates of the lab-based systems, which are ideal conditions, fantastic. They're all based on a hydraulic loading rate of roughly 2 to 2.5%. And we're still yet to see any sort of field scale study of a conventional bio showing TN removal concentration reductions of anything greater than 33%. So to achieve, say, a 45% load reduction target, we obviously need to get a whole bunch of water draining through the filter media and obviously only a little bit being allowed to overflow. So in that regard, I'd suggest that bioretention systems should be essentially larger than what music predicts. In the States, we see system size at what, Michael, 5 to 8%.
5%, pretty typical.
Certainly not as small as what we see in Australia. And I think that might be a key contributing factor as to why we're seeing conventional bioretention systems actually failing, is that they're just being asked to work too hard. And they're just getting, I guess, overloaded with flow maybe, but probably more importantly, the sediment. and not being appropriately maintained.
Yeah, and if you look at the 33%, 35% TN removal on a concentration basis and your 1% of the catchment, of course your ET is not going to get you to the magic 45. But if you're at 3, 4, 5%, you'll certainly be a lot closer to that 45% load reduction without exfiltration. So, yeah, I think there needs to be something looked at about how we size our bioretention systems, given that they're much smaller than anywhere else in the world.
Hey, look, we're going to have to wrap it up. We've been going for an hour 40 and we've still got 86 people dialed in. So thank you everyone who has participated and sat through this webinar. If you'd like to ask myself or Michael some further questions, I'm going to reshare my contact details. I'm not sure what you can see there, Michael, but they're essentially our contact details.
Yep.
If you've got further questions you'd like to ask Michael or myself, please do so. Our email addresses and contact details are essentially right there on the screen. So again, if you've got anything you want to ask us, sorry, I'm stuffing this up, but if you'd like to ask myself or Michael any further questions, yeah, please do so.
And also any comments, any things you'd like to see talking about, anything, any content or any ideas for new webinars, yeah, please just reach out, let us know. Yeah, this one's been quite good, a lot of attendances, which is great. So yeah, anything else you want, just let us know.
Again, thanks everyone for dialing in. All registrants will get a copy of the slides and a link to the recording as well. So if you'd like to watch it again or just check out the slides or do the research of those papers I referred to, yeah, please do so. But look, without further ado, Michael, thanks for your time.
Thank you, Brad, and thank you to the host with the most, Mr. Brad Dalrymple. Thank you, and I think everyone's fallen out of it. So, you know,
cool.
it's been really good.
Thanks, guys. Be
Thank
good.
you.